Thank you, Emma, and thanks for everybody for being here. I suppose that it was not so easy to get up today, for me neither. First of all, thanks to the organizers for giving me this opportunity to present part of my research dedicated to metallic elements in the environment, metallic elements from natural sources. Maybe I should also add to this title of my presentation that we are talking about natural sources of metallic elements in the environment. So before I start, I would like to, the ultimate goal of my presentations today will be to convince you, but I'm not really sure if I have to do this already. But I will try to convince those who are not already convinced that ultramafic rocks and geosystems in general are really interesting objects to study. And we already hear plenty of presentations about ultramafic rocks. Through the study of these rocks, we can trace the evolution of the Earth's mantle. Probably everybody already deal or heard about the ore formation during weathering of ultramafic rocks. I mean laterite, nickel, and cobalt ores, as well as chromite or magnesite, which is recognized as a critical ore by the European Union. Ultramafic geosystems are also object for study for botanists because there are specific plants growing on these areas. I mean the plant hyperaccumulators that could accumulate up to 1,000 milligram per kilo nickel, for example, in the tissue. Of course, yesterday there were plenty of talks about and posters about carbon capture and storage, and we heard that ultramafic rocks are perfect materials for carbon capture and storage. And my talk will be mostly focused on the mobility of metallic elements from ultramafic geosystems, but I will try to touch a little bit also other subjects. So at the beginning, I would like to say some general things about ultramafic geosystems. I mean ultramafic rocks and associated soils. These geosystems are characterized by some peculiar chemical properties, such as high magnesium and calcium content, also a valuable part of these chemical elements. Low nitrogen and phosphorus content, which is not, which makes these areas not favorable for plants in general. And that's why we often observe a distinct endemic plant community in these areas. And here we have two examples from French Massif Central. A typical ultramafic site, not much of vegetation, only grass. And on the right side, you can see a characteristic fern growing on serpentinites in Poland. And what is the most interesting for me are the elevated concentrations of metallic elements. I call it the ultramafic triad. I mean nickel, chromium, and cobalt. And yeah, the first thing when I deal with ultramafic geosystems, I mean soils and rocks, it's a characterization of rock. I work a lot with soil scientists, and I always have to convince them that this is really important to characterize the parent rock. Yeah, because in general, in the most simplistic way, we can say that ultramafic rocks are dark because composed of over 90% of dark mafic minerals. And these rocks are, of course, rare on the surface and quite rare within the continental crust. But in more, and I always try to explain to people that mineralogy really matters. I mean, mineralogy, mineral composition of parent rocks, because we can have very different types of ultramafic rocks, and it's not the same. Probably all of you know this triangles, this classification triangles. So I won't go to the details, but the most important thing to say is that peridotites and serpentinites, the two main types of ultramafic rocks, it's not so common that these rocks occur on the surface and continental crust. Most often we observed different varieties of serpentinizite peridotites or pyroxenites. And what is important for me is to find out which minerals of these rocks are responsible for nickel, chromium, and cobalt concentrations, and this is slightly different for different types of ultramafic rocks. And on these diagrams, we can see that pyroxenes are the main chromium-bearing minerals, although in spinel group minerals, we can have an order of magnitude more chromium than in pyroxenes, but these cases are much rarer than pyroxenes. And the olivine is the main carrier of nickel in these rocks. And as serpentinization progresses, it slightly changed the composition of minerals, because we can see that relicts of pyroxenes and olivines mimic the chemical composition of parent minerals. But as serpentinization progresses, we see much more homogeneous nickel and chromium composition of serpentine group minerals, very close to the bulk composition of rock. So I think that's all about the rocks. And right now, some information about ultramafic soils. It's a common name for soils. Generally, botanists don't really care about parent material. Yeah, so because the similar type of vegetation grows on peridotites or serpentinites. And that's all. Yeah, but these soils offer the possibility to study the mobility of metallic elements from natural sources, and it's also a hotspot for biodiversity. I already mentioned the word hyperaccumulator. These are plants able to accumulate metallic elements, and it's especially interesting in case of nickel, because it's around, we know around 500 plant species with hyperaccumulating properties, but most of them, around 450, are species that are nickel hyperaccumulators, and of course occur in the ultramafic areas. And these plants are often used for phytoremediation or phytomining. So that's why, and can even accumulate up to 30% of nickel in the tissue. So on the right side, you have examples of different plants. I'm not good at plants. I had a PhD student, and I was never able to remember these names for all these plants. But fortunately, we have students. Okay, so right now I would like to present some data about chemical composition of ultramafic soils. So here on this diagram, you have concentrations of nickel and chromium in the surface layer of ultramafic soils from all over the world. And I also put some lines here, which means that these are regulatory guidance values determined by in different countries. Almost in each country, there exists a law defining how much a metallic element could be in the soil. It's allowable in the soil. this soil to be cultivated. So here you can see that we have, and I will refer to the median world regulatory guidance value, which for nickel is around 100 ppms, 100 milligrams per kilo, and for chromium is 250. And we see that nickel and chromium concentrations exceed these values, and this is, yeah, I mentioned here the Polish example, but it's also for regulatory guidance values, the mean median world value. And in some countries, these guidance values are also determined for industrial in soils, I mean, industrially used. And we see that even for this limit, which is much higher, 500 ppms for nickel and 1000 for chromium, quite a few soils from all over the world exceed these values. And so the median worldwide, the median content of nickel and chromium in ultramafic topsoils is of order of magnitude higher than the allowable concentrations in soils. And I also put the values for average content in surface soils in upper soil horizon, and you can see that it's much higher in naturally enriched serpentine or ultramafic soils. This is the diagram for nickel and cobalt. So we see that for cobalt, the story is nearly the same. We have also, of course, much lower limits for cobalt because it's not as abundant in ultramafic soils and rocks. But almost for each soil, these limits are, at least for arable soils, these limits are exceeded. Okay, so, but we should remember that ultramafic geosystem soils, this is a natural thing. So the increased metal concentrations is not the result of pollution, but it's a kind of geochemical background. So there is no reason for the remediation of these soils. It wasn't even possible, but at the same time, it's not really easy to find an ultramafic soil that does not overstep the limits for these three elements, this ultramafic triad. But of course, we should remember that the total concentration of metallic elements in soil does not determine the mobility or bioavailability of these metallic elements. So the second part of my talk today is about mobility and some how differences in mineralogy of ultramafic rock might be responsible for some difference in mobility of metallic elements. So first of all, in soils, there are some differences whether this soil was formed on peridotite and serpentinite. These are morphological and, let's say, visual differences even. And this is because of the mineralogy again, which is important, but you know it very well. Because olivine is a major iron-bearing mineral in peridotite, but in serpentinites, I mean proper serpentinites, the major iron-bearing mineral is magnetite. Yeah, so we know that magnetite is quite resistant to weathering, whereas olivine is quite prone to dissolve in the soil conditions. So it was observed by Alexander that iron is more readily released in soils from peridotites than in soils from serpentinites. And we have higher concentrations of iron oxides in soils on peridotites, and also the color of the soil is more red. Yeah, so and therefore we And it comes the hypothesis for the research of metallic mobility, because as in peridotites, we have olivine and pyroxene, which is less resistant to weathering than serpentine group minerals. We expect that the mobility of metallic elements could be or should be affected by the type of the rock, and should depend on the degree of metamorphic alteration of the primary peridotite. So we ask the question whether the type of ultramafic rock affect the bioaccessibility of metallic elements in ultramafic soil. And for this, we studied 6 ultramafic sites located in Poland, where the parent rocks were different, and from serpentinite peridotite through serpentinite with relics of primary textures and primary phases, up to proper serpentinites composed almost exclusively of serpentine group minerals. And here I ask you to remember the color code, which is red for peridotite, orange for serpentinite with relics of primary phases and textures, and green for proper serpentinite. Yeah. Of course, the soils were quite similar, except for the stage of development. Sometimes it was only 20 centimeters, but some soils had almost 1 meter or even more than 1 meter thickness. And we always sample the soils from the upper position in the top of this top of sequence, because we wanted to look at the really similar soils, and just to eliminate the other soil forming factors, only look at the parent rock. Sorry for this diagram, but I know that there is a lot of information, but what I wanted you to keep in mind is that, okay, so this white color means that this is the total concentrations of nickel, chromium, and cobalt in soils, and the gray color means that this part of this total concentration is potentially bioavailable for plants. This mobility assessment we usually do using chemical extraction experiments. So we put the sample into the solution, and in this case it was EDTA solution for some time, and we analyze the extract, the leachate, and in this leachate we saw certain proportions of metallic elements, which means that it could be bioavailable for plants. And what I wanted you to see here, that in the case of chromium, we observe really low mobility. You can see that only up to 4% in the worst case of chromium is mobile and could be bioaccessible for plants. Whereas for nickel and cobalt, it's the other story. You can see, yeah, you can see, for example, in this first site, it goes up to 14% of total concentrations. And when we keep in mind that the total concentration was around 2,000 milligrams per kilo, so we have here 300 milligrams per kilo potentially available nickel. And if you remember that the allowable concentrations, but for the total soil is around 100, we see that it's much more than plant can absorb, than it's allowable in soil, in total soil. So there is a problem, yeah. But yeah, let's move in a more detail to the. So we see that, okay, chromium is not mobile, so it's okay. But in the case of nickel, we see that in the soils derived from peridotites, nickel it's much more mobile than in soil for from serpentinites. Yeah, we see that we have easily up to 15 or even 20% of nickel available in soils on serpentinites, peridotite, and serpentinites with relicts of primary phases. Whereas in proper serpentinite, this value reach only up to 7%. I am not talking about organic horizon, because we see that this site 5 is characterized by quite high mobility of nickel in organic horizon, but we exclude for this discussion the organic horizon because of differences in organic in some difference in a plant species in vegetation from site to site. So we only discuss the mineral horizon. And in the case of chromium, we see similar behavior. Yeah, generally more mobile cobalt in soils derived from serpentinized peridotite. And why is this happening? I already told this, I think, during presenting the hypothesis, because in peridotite we have olivine, which is the major component of partially serpentinized peridotite. I've written here 20%, but in some samples it was up to 50% volumetric percent of olivine in the rock, and average concentrations of nickel in olivine was around 3,000 milligrams per kilo, whereas in serpentinites, the serpentine group minerals and spinels are responsible for nickel, but in much lower concentrations of nickel are observed for serpentinites. Okay, so this could be quite easily explained. And in the case of chromium, so yeah, when we want to answer the question whether the type of parent ultramafic rock affects the bioaccessibility of metallic elements, we can say that in chromium there is no clear relationship between the type of rock and the soil, because the chromium-bearing minerals are always the same and highly resistant to weathering. So we have not mobilization of chromium. In case of nickel and cobalt, a higher mobility was observed in serpentinized peridotites than in serpentinites. Proper serpentinites without any relics of phases and textures. And why is that? We can say that maybe during serpentinization, nickel and cobalt were once mobilized already and trapped again by the phases more resistant to weathering, such as magnetites and serpentinites, than this primary olivine. Okay, so, but it was the potential mobility, I mean, estimated using chemical extractions. But what about the real mobility? And for having an information about the real mobility, we have to analyze plants growing on the ultramafic soils and ultramafic geosystems. And these let's say 4 diagrams show the concentrations, the content of nickel, chromium, and cobalt in plants growing in ultramafic areas. And we see, I already told that there are plant hyperaccumulators that have more than 1,000 milligram per kilo of nickel in the tissue, in the upper parts of the plants, not in the raceme. But also we observe elevated concentrations of nickel and also in the lesser extent chromium and cobalt in soils, in even edible plants. Yeah, and it's not rare that the concentrations of nickel in these plants exceeds the allowable concentrations of nickel, but determined for total soil concentration. So we see that in real plants, in real sites, the concentrations of nickel could be much higher than those allowable by legal acts. So to further confirm our hypothesis about relationships between rocks, different types of rocks and soil and the mobility of metallic elements, we started to analyze plants from two contrasting sites having the contrasting lithology. I mean the soil on serpentinized peridotite and soil on proper serpentinite. These soils, these sites were characterized by similar vegetation cover. So that's why we choose them. So first of all, it was a totally different parent rock, parent material, and the same, or quite the same or similar vegetation. So we've done another extraction, DTPA, which is a little bit less aggressive, and generally for the plants growing in soil formed on serpentinized peridotite, we observed that these extractable contents of nickel are generally higher than the nickel concentrations in plants, which means that, okay, this extraction estimates is a good estimate for potential mobility. But when we analyze the plants from the other side, so the site where nickel and chromium and other elements are less mobile than from the site on serpentinized peridotite, we saw that here the extraction results were much lower than the content of nickel in plants, and also the concentrations of nickel in the plants from this site was higher than the concentrations of nickel in soils from plants. Sorry, from soils on partially serpentinized peridotite. So there is a problem because, yeah, these concentrations of nickel in plants did not confirm the extraction results. But we also look at the physicochemical composition of the soils, and we saw that there is much more exchangeable magnesium and calcium in soils developed on serpentinized peridotite than in soil from serpentinite. And this contrasting behavior could be due to this calcium and magnesium, because plants prefer to absorb calcium and magnesium than nickel, even there is much more available nickel in soil on peridotite than in serpentinite. And these two cations are favored by plants and fill the available sites, which results in a lower nickel intake despite the higher abundances in soils on peridotite. So again, could we confirm the hypothesis? I think yes, but because these increased levels of magnesium and calcium in the soil on peridotite is directly related with the properties of the rock, because we have much more available magnesium that comes from the weathering of olivine, and the only calcium-bearing mineral was amphibole, present only in soil derived from peridotite. So our research hypothesis was proven finally. And okay, and right now the third part of our research on mobility of metallic elements, which is quite new. We just started 2 years ago to study the mineral carbonation, but not only the mineral carbonation as a method for fixation of carbon dioxide, but we are also interested in the fate of metallic elements during this mineral carbonation, because we know that I think that I already convinced you that ultramafic rocks and associated soils are a source of metallic elements into the environment. And we saw on one hand that ultramafic rocks are perfect materials for carbon capture. But we also know that these soils, these materials, these rocks and associated weathering covers and soils as well are rich in some metallic elements. So our aim is to identify the fate of metallic elements during carbonation of ultramafic rock. We saw that through the research of mobility of nickel in soils, we saw that this element is quite mobile. So what about this carbonation? And for that, we've chosen 3 types of rocks for the experiment, because we started from a quite simple experiments of mineral carbonation, and we choose for our study 3 types of rocks. 2 were the partially serpentinized peridotites, indicated here as site 1 and site 3, and the third rock was serpentinite, composed exclusively, almost exclusively of serpentine group minerals. So here are the X-ray powder diffraction patterns of these 3 rocks. We see that rock 1 and 3 are quite similar, and a rock, and of course with some different mineralogy of proper serpentinite. Okay, so we also, for us, it was really important to identify prior the experiments, the main nickel, chromium, and cobalt bearing phases. So in case of nickel, it's not surprising, olivine, serpentine group minerals, spinel, and some sulfides. For chromium, it was spinel group minerals and clinoflora, and for cobalt, we identified sulfides containing up to, let's say, 15% of cobalt. And we done several experiments after different conditions. Generally, these experiments were done on the pulverized material under 50 microns. So we put the material with water only into the reactors. And I said it was several experiments. We tested some different conditions of the temperature and pressure from 50 degrees Celsius to 185, and the pressure was from 20 bars to up to 150. After the experiment, we took the leachate, the fluid, and we analyzed the composition of the leachate, and we also analyzed the products of this mineral carbonation experiments. I will focus on these 2 experiments because they appeared to be the most effective for carbonation. Our aim of this experiment was not to really care about how much carbon dioxide we will be able to store, but it was to produce as much as possible of the product, of the carbonate, in order to analyze what's inside. Yeah, I mean, what's inside, whether there are some metallic elements in this newly formed phase or not. So first, the results of fluid analysis, which indicate that the most mobile from this ultramafic triad is nickel, reaching up to, let's say, 18 milligrams per kilo in the leachate. In case of chromium, it was much less. In case of cobalt, it was an order of magnitude lower, but of course, cobalt concentrations in rock are also lower. Okay, so what's next? We characterize the mineral carbonation products, and for before, of course, and after the experiment, and based on the Rietveld refinement, we estimate that the magnesite content in the sample after the experiment in the serpentinized peridotite from the site one, first locality was 14%. In the case of serpentinites, it was around almost the same amount. But what was surprising that for the third rock, we obtained almost 50% of magnetite. It was quite surprising. Before this rock from the site 1 and the site 3 were almost, let's say, very similar in terms of mineral and chemical composition. And this last diffraction pattern shows that during the experiment a little bit longer in 100 bars and 185 degrees, we observe a almost complete dissolution of forsterite and olivine and the formation, of course, of magnesite around 50% of sample. Okay, so we cannot explain for now these differences. I mean, why this advanced carbonation occurred for peridotite from the site 3 and not for the site 1. We suppose maybe this is because already some carbonates were present in the sample from the third site and served as a center for nucleation and carbonate crystallization, or maybe this phase assemblage was prepared for this carbonation naturally. We do not know, maybe because of the presence of some secondary phases in the peridotite from site 1, like iron oxide hydroxides or silica acting as a reaction inhibitors. This we don't know, but we think about this. And how the material looked like after the experiments. So I will present only the data for this partially serpentinized peridotite from site 3, because this carbonation was the most effective in this case. So you can see on the left starting material, even at lower at the conditions of low temperature and pressure, I mean 50 degrees, we observe already the formation of carbonates, small crystals of magnesites, and at higher pressure and temperature, we observe quite a lot of crystals of magnesite, and these crystals they constitute a kind of matrix for this sample after the experiment. During waiting for the results of chemical analysis, we also tried to find out what is about the nickel concentrations and the other metallic elements in naturally occurring magnesites, which are quite frequent in analyzed sites. In Poland, there are some magnesite deposits exploited. So we measure the concentrations of nickel in our samples, and we saw that for some magnesites, this nickel concentration could be quite important, up to 1,000 milligrams per kilo. So it could mean that in these products of carbonations, nickel could also be found in the structure of magnesite. For the other carbonates, we did not see really important concentrations of nickel, because we also analyzed not only magnesite but also dolomite and calcite. But the most interesting thing that we saw after one of the experiments was this kind of structure. So this was in the experiment where almost all thiolite was gone, the forsterite, so it was gone. And we observed the formation of silica in these botryoidal forms and the formation of a layer composed most probably of secondary of phyllosilicates. But what was the most important for us? It was the nickel content reaching up to 30% of nickel oxide. So this space is a kind of equivalent of garnierite, which form naturally as a result of weathering of ultramafic rock, and it can serve as a nickel ore. So to sum up my this third part of my talk, after the analysis of fluid and leachate after the mineral carbonation experiment, we see that some part of nickel could be mobile during these experiments, and most probably this element was released from the olivine structure, and it remains partially in the solution. But as you could see, this element could be also bound in newly formed phases. We also saw some concentrations of nickel in the magnesite, but yeah, we didn't analyze on a our samples using a microprobe. This was SEM semi-quantitative analysis. What was unexpected is that one of the peridotites was more prone to carbonation than the other, and yeah, the first explanation is mineral composition, and but not the major minerals, because these major minerals were the same. What was more important is trace mineralogy, and we have some open questions arriving from this research. This question is whether it is possible to that by choosing the right conditions for mineral carbonation, we can also extract metallic elements. So I mean, I know that my PhD student doesn't like this sentence, but we could kill two birds with one ultramafic stone, maybe. On one side, we could extract nickel, and the other capture CO2. Maybe it will be possible in the future. And just to conclude that the mineralogy really matters, we observed that even small differences in the composition of the starting material can affect the efficiency and the distributions of metallic elements, and the really individual approach is necessary to each sample and to each experiment. So with that, I will go back to the second slide. And I hope that I convinced you that these ultramafic geosystems are really interesting, and not only because of the mobility of metallic elements, but there are also plenty of other subjects that could be studied. Yeah, and at the end, I would like, because this was research done by not only me, of course, I had plenty of colleagues who helped me during all these experiments and analysis, and I want to thank them all here who influenced not only this research, but also my career, I would say. So thank you.
Oh, thank you very much. It's always exciting to see so much very new and unpublished data. So would anyone have any questions? So early on the last day.
Well, I've got maybe one to get started. Your extraction technique, ED, is it P or TA?
ETA, yeah.
How does that compare to sort of leachability and mobility in nature?
Generally, it's it's we can say it's a worst case scenario. Yeah, so it means that no more than this extracted by these halating agents will comes to the plant.
Okay.
So it's quite aggressive. So DTPA it's less, maybe more suitable for this kind of analysis. But we wanted just to compare the rocks, so we choose this one.
Okay. Okay. Thank you. Okay. Yeah. Question in the middle.
Thank you for the talk. Are there any known, getting back to the plants section, are there any known ill side effects health-wise for people or animals or livestock living on ultramafic rocks? We have a few in Ireland as well, so just wondering.
Yeah, this is I don't know if I understand well your question, but generally plants have two abilities to live there. So one is the hyperaccumulation and the other is exclusion. So they just keep the metallic elements in the resins. But what is observed generally, these areas are quite barren. It's not really, they are not really favorable for agriculture. But of course, with today's life, these areas are also cultivated. So people try to use some fertilizers to increase the, to give the plants the nutrients, because the main problem for plants is maybe not even nickel, chromium, and cobalt, but the scarcity of phosphorus and nitrogen. So that's why they don't want to really grow there. And even if they did, they are smaller, and this is a kind of adaptment. Even in some, because the, let's say, temperate climate ultramafic sites are not that bad. In the tropical areas, it's much worse because the concentrations, the weathering is faster, more intensive, and we have much more nickel in these areas. And there are even some animals that could live there and could have up to several % of nickel in the body.